Okay, so in this video, we're going to take a look at work and how it relates to energy. So to start off with, let's talk about two laws that we need to know about energy. So the first is the law of conservation of energy that states that energy cannot be created or destroyed, only transferred into other forms. And if we look at our Sankey diagram that we've looked at drawing previously, we can see it starts off with 100 joules of electrical energy, and it ends up with 100 joules of kinetic energy and 900 of thermal energy. So we can see the total energy at the start is 1,000, and the total energy at the end is 1,000. So we haven't created or destroyed any energy, so that's fine. So the second rule, the second law of thermodynamics, in fact, describes that over time, energy will transfer to less useful forms. So any time you transfer energy from one form to another, you're going to produce less useful forms, and that's often in the form of thermal energy. Okay, so those are our two kind of laws of energy. So work is specifically a type of energy transfer, and it's when energy is caused to transfer by a force. And what we say then is if a force has done that, the force has done work. So I'm going to give you a scenario. So when someone stretches a slingshot, describe the useful energy transfer that the force causes. So we don't really care about the waste in here, the useful energy transfer. So pause the video on your booklets, see if you can write down the energy transfer that is useful. Okay, so now you should have written down what you think the energy transfer is. So let's take a look. So when you stretch a slingshot, you're applying a force that transfers chemical potential energy in your muscles into elastic potential energy by stretching out the elastic. That's the energy transfer, and you're doing work to make that transfer because you're applying a force and you're pulling it back. So when the slingshot is released, describe the useful energy transfer that occurs. So again, pause the video at this point, see if you can describe that too. Okay, so I'm assuming you've done that. So let's take a look. So the force from the elastic or the stretch material transfers elastic potential energy into kinetic energy. That would be the useful energy transfer. Okay, so let's talk a bit more about what work is. So we've seen that it's when you use a force and you cause energy to transfer, but there's a little bit more to it than that. So we can actually calculate how much work we've done if we know what force we've applied and the distance over which we've applied it parallel to the force. So if we're going to do some work on an object, we must apply a force to the object, and the object must move parallel to the force. Okay. So let me give you an example. This is a person holding a stationary plank. Are they doing work? Explain your reasoning. So you're going to pause the video. Are they doing work? Yes or no? And explain why you think your answer. Okay, so I'm assuming that you have paused the video and you've written what you reckon is going to happen. So let's actually see. So the correct answer is no, they are not doing work. So yes, they're applying a force, but they are not moving parallel to the force. Therefore, no work is done by that force. Okay, so a force that acts in a lot of situations is friction, and it's any situation where we have two surfaces sliding over one another. And we can see in the diagram the sort of the source of a frictional force, the surfaces rubbing against one another. So what form of energy does friction transfer kinetic energy into? So pause your video, write down what you think it is, and then we'll take a look. All right, let's take a look. So friction transfers kinetic energy into thermal energy, which it sends out into the surroundings. So it's increasing the energy of the surroundings, but it's decreasing the energy of the object itself. Okay, so we're going to see how work done works by considering three scenarios. You've got an object sliding across banana skins, which are very slippery, at least in cartoons anyway, sliding across wood, which is quite slippery, and sliding across a carpet, which is not very slippery at all. So these three objects are all going to start at the same speed, which means they all start with equal kinetic energy. The only difference between the scenarios is the size of the frictional force. So we're going to think about this in terms of work, and remember work is force times distance. So we're going to consider them with all starting with the same kinetic energy, and that means that the frictional force is going to have to do the same amount of work in each case to stop the object, because what it's effectively going to have to do is turn all that kinetic energy into thermal energy. So the frictional force has to do the same amount of work to stop all three of the objects because they start with the same kinetic energy. So using this equation, we can start to think about how long the object would travel before the frictional force has done enough work. So what you're going to do is pause the video now, and you're going to state which object would travel the furthest before it stops and explain why that is. Okay, so I'm assuming you've done that. So the object sliding on banana skins would travel the furthest, which is probably intuitively what you reckon. So the reason is its frictional force is the smallest, so it has to travel a longer distance to do the same amount of work and transfer all that kinetic energy to thermal energy. Okay, so we're going to have a look at a few example questions that, again, I'm going to ask you to have a go at these first, and then we can go through them. So the first one, a block sliding across the surface starts with 20 joules of kinetic energy. If the frictional force is 8 newtons, calculate how far it travels before it stops. So pause the video now and have a crack at these three stages. All right, so first of all, the equation we're going to use, work done, is force times distance. We're going to have to do 20 joules of work to stop the object. So we want to calculate distance, so I'm going to divide both sides by distance to get our like I just want to calculate. Our work done is 20, our force is 8, giving us a stopping distance of 2.5 meters. Okay, so next question. A car has 1,200 joules of kinetic energy. The engine then applies a force of 6,000 newtons for a distance of 200 meters. Calculate the final kinetic energy. So again, pause the video, have a go, and then we'll go through it. All right, let's take a look. So first thing we're going to do is going to calculate how much work the engine has done. So it's going to be 6,000 times 200. So an engine does work to increase the kinetic energy. So the kinetic energy is going to be adding together those two energies. And then what we're going to do is, once we've got our final answer, we're going to round it to an appropriate number of significant figures. So if we look in our question, 1,200 is 4 significant figures, 6,000 is 4, 200 is 3, so I'm going to give the answer to 3 significant figures in either of those two forms you can see there. Okay, final question. 1 horsepower is 746 watts. So watts is the unit of power, so you're going to need an equation for power to do this question. So 5 horses pull a cart for 10 seconds, in which time it covers a distance of 120 meters. Calculate the force provided by 1 horse. So again, I want you to pause the video, have a crack at these. You may need to look up your equation for power in able to proceed through this question. All right, let's take a look. So what I'm going to do is calculate the energy supplied, or the work done, by the horse. So power is the energy divided by time, or energy transferred divided by time. So in this scenario, we're transferring energy by doing work. So I've replaced the E with a W. So if we do power times time, that means the horses have done a total work of 7,460. 5 horses, we multiply that by 5. To get the total force, we're going to do work done divided by the distance. And then we want the force from 1 horse, so we're going to divide that by 5, and that completes looking at this question and looking at work and energy.